In this video, we're going to continue our discussion of runtime organization by talking about how compilers handle global variables and heap data structures. Let's start by talking about global variables. The basic property of a global variable is that all the references point to the same object. That's what it means to be global. And for this reason, we can't store a global variable in an activation record, because the activation record, of course, is deallocated when the activation completes, and that would deallocate our global variable. So the way global variables are implemented is that all globals are assigned a fixed address once, and these variables with fixed addresses are said to be statically allocated because they're allocated essentially at compile time. So the compiler decides where they're going to live, and then they will live there in all executions of the program. And depending on the language, there may be other statically allocated values, and we'll actually see some later on, but they behave just the same as global variables. So adding global variables changes our runtime organization picture a little bit. First, we have the code as before, and then immediately after the code is typically all of the static data. So these are the global variables and other static objects, things that have fixed addresses for the duration of the execution of the program. And then the stack comes after that. So the stack will start at the end of the static data area and grow towards the end of the program's allocated memory. Turning now to the heap, any value that outlives the procedure that creates it also cannot be stored in the activation record. Let's take a look at this example. So here we have a procedure foo, and let's take a look at the activation record or frame for foo. And let's say that the foo allocates a bar object, and that we're going to store that object in foo's activation. And now when this method returns, of course the activation record will be deallocated, and so the bar object will also go away. But that won't work here because notice that the dynamically allocated object, the object we allocated during the execution of foo, is also the result of foo. And so this has to be accessible to foo's caller after foo exits. And so what that means is that this bar object and all dynamically allocated data have to be stored someplace other than the activation record. And languages with dynamically allocated data generally use a heap for that purpose. At this point, we can summarize the different kinds of data that a language implementation has to deal with. First, there is the code. And in many languages, I shouldn't say most, in many languages, the code is a fixed size and read-only. That means that the compiler creates all the code that will be used in the execution of the program, and that can be allocated once. I should say that there are many languages also where this is not true, and code can be dynamically created at runtime. The static area would contain data with fixed addresses, and this would be things like global variables. And this is also typically fixed size, but it may be readable and writable as opposed to the code, which you generally don't want to be able to write. And then a stack is used to contain an activation record for each currently active procedure, and the activation record is generally fixed size, so each activation record for each particular kind of procedure has a fixed size, and this will contain all the local information, the local variables and temporaries needed to execute a particular activation. And finally, the heap is for everything else. So the heap is just for all the data that doesn't fit into one of these other categories. This includes all the dynamically allocated data. And if you are familiar with C, the heap in C is managed by the programmer using malloc and free. In Java, you have new for dynamically allocating data, and then garbage collection actually takes care of reclaiming data from the heap that's no longer used. Now, many language implementations use both a heap and a stack, and there's a little bit of an issue here because both the heap and the stack grow. And so we have to take care that they don't grow into each other and step on each other's data. And there's a very nice and simple solution to this, and that is to start the heap and the stack at opposite ends of memory and let them grow towards each other. So let's take another look at our runtime organization picture. And just to review, first we have the code, and then we have the static data. And then we have the stack, which grows towards, in this case, the high address allocated to the program. And notice that the stack doesn't necessarily just grow. As procedures return, the stack will also shrink. So as the program runs, the stack will get bigger and smaller depending on how many procedures are currently running. And now the heap will start at the other end of memory and grow towards the low address. And so as we allocate objects, we'll be allocating from the back of memory or the end of the memory allocated to the program up towards the top of the stack. And if these two pointers ever become equal, and what are the two pointers? Well, we have a stack allocation pointer that says where we're going to allocate the next stack frame. And we have a heap allocation pointer that says where we'll allocate the next object if we have another dynamically allocated object. As long as these two pointers don't cross, as long as they never become equal, then the program has memory to either add another stack frame or another dynamically allocated object, and the program can continue running. If these pointers ever become equal, then the program is in fact out of memory, and at that point the runtime system will abort the program or try to get more memory from the operating system or take some other course of action to deal with the fact that there is no more memory. But as long as these two pointers don't cross, notice that this design allows the heap and the stack to share this data area in whatever way suits the program best. So this same design without any changes will work for programs that need a lot of heap and only a little stack, and for programs that need a lot of stack and only a little heap, and things that have a rough balance between stack and heap, as long as they don't exceed the total memory allocated to the program.